All right. So, welcome back. Today we want to continue our discussion on multi-core systems. If you remember, last time we talked about the problems that we're going to face. We started with coherency issue, and we show you what's the coherency issue is. And then we start talking about the solution and said that, okay, the main solutions that we are looking at is snooping cache. And we kind of gave you an example of a simple MI coherence policy, which essentially you either have the data or not. And we show that how they can fix this coherency issue, which, this Z is being, saved into private cache. One of them updates this and the other doesn't. And as a result, it gets an incoherent copy. And we show that with snooping, we can essentially invalidate this line. And then the next time that the other core wants to read it, it reads the updated value from the memory. That was kind of like the basic idea. Then we start kind of optimizing this. The first thing that we did was adding a shared state, because shared can be very helpful, because if everybody wants to just read things, there is no reason that kind of they keep invalidating themselves. So we introduced this S state, the shared state, in order to improve the efficiency of this model. And then we started talking a little bit about how do we further improve MSI. And the first thing that we introduced was E state. I'm going to complete that, and then I'm going to add another two, which is called an O state and an F state, so that together we're going to have this 6 states cache coherence policy. The motivation for adding this exclusive state was, if one core only has the data, they don't need to really broadcast it to anybody else, as long as nobody else wants to read it, right? So we only broadcast that I have something unless only if somebody else wants it, right? So we introduced the idea of MESI protocol, which essentially we are adding this E state, which the difference between MESI and MSI is that when we are in I and everybody is in I and we want to move to S, instead of moving to S, we're moving to E, which means that that particular core is the only one who has a copy of that data. The usefulness of this is that from E, one can move to M with what we call a silent update, which means that they don't need to broadcast anything to the snooping bus. Okay, that's really the benefit of this. Okay. So they're giving you an example. Let's say we have something like R1, RW1, R2. So initially, all of them are in the invalid state. Then this R1 comes in, and as I said, with MESI, since all of them are in I, instead of going to S, we go to E, and everybody else stays in I. Then if we want to go to right one, then this one goes to E, and then as I said, the important thing here is that no broadcast happening here. Okay, that's really the difference. And then again, everybody stays in I. And here, if R2 wants to read it, this one goes to S, and then there will be a write back here, and then this one goes to S, and this one goes to S, right? I'm sorry, this one goes to I. So that's really what is happening here. For example, if we had something like R1, R2, then the states would have been I, and then E, I. And then once this one comes in, this E no longer is exclusive. So now this E needs to go to S, and this one also goes to S. Right? So that's kind of like the idea. Any questions? Okay. So let's do another optimization, and this time we want to introduce the idea of another new state called O. So for example, let's say we have a scenario like this, that one core is in M, okay, and all the others are in I, okay, and now a new core wants to read this data, okay. What we usually do at this point is that if everybody M and then I just said that this has to write back to the memory. And then this core needs to read it from the memory and then goes to S, and this one also goes to S, right? So there will be kind of a round trip to the memory and from the memory in order to read this data, okay? And I think somebody actually mentioned this last time, that this seems to be like a very long process because access now needs to go to the memory. But if you actually think about this, that this core already has this data. So maybe we can actually forward it to this other cache, right? In this other core. So that's the idea of what we call an O state. The O state basically does this for us, that if you're in M and somebody wants to read this data, this M, instead of going to S, it goes to this new state called O. And this O is basically the one that has the dirty copy of the data, okay? And anytime that this O wants to go back to I, only at that time you're going to write back the data to the main memory, okay? And then the beauty of this is that O can forward data to other caches, okay? So if somebody wants to read the data, it reads it from the O. So O is actually forwarded to the other cache. So if I have like a 2-core system like this, if this was in O, instead of going to the main memory and then main memory forward this data, we can have the O state, which now the O state basically forwards this data to the other cache. So it becomes a cache-to-cache kind of forwarding rather than going to the main memory and coming back from the main memory. Okay, that's how we can actually save a lot of bandwidth and save a lot of latency, because we kind of saving 2 kind of packets going to the main memory for the write back and for the forwarding, and then make it much faster. Okay, any questions here? It does. It stands for yes. I don't know what it stands for something. It'll come back to me, but I'll let you know. So let me give you an example. Let's say we have everybody in I initially, and then let's do the same R1, W1, R2. So first one, so first of all, for example, for this one, we don't have E, but of course you can have MOESI, okay? As I said, these are kind of like depending on different macro architecture, you can add and remove these states. So you can have MOSI or MOESI, okay? So for now, let's assume that we have only O in addition to S and M and I. So if from R1 we go to W1, we go to the M state. Sorry, for the first one, we go to the S state because we don't have E, and this one goes to I and I for this one. Now from R1 we go to W1. So from this we go to the M, okay? But now from W1, if there is an R2, what is happening is that from here we go to the O, and this one goes to the S, okay? I keep making this mistake. Should be I. So what is happening compared to MSI or MESI is that this used to be write back and then going to the S, but now I don't do the write back, I just go directly to the O, and there will be some form of a forwarding happening here between O and S, okay? We usually in your questions, homeworks, stuff like that, we give you notations. For example, say that, oh, if you put in a star, it means write back. I don't know, if you do the plus, it means forwarding. I'm just showing, like, I'm creating this random kind of annotations. It's not like a specific rule or anything, okay? So basically what is happening here is that there's some form of a forwarding happening here, okay? If we had MOESI, the difference would have been that this would have been E, right? So the first one would have been an E, and from E we go to the M, and from M to O, okay? So we can mix and match all of these things together. Any questions?
So, like, what specific hardware component to what specific hardware component does it forward from into?
The question is, when we are doing the forwarding, what is really happening in hardware? consider something like this, that we have our cores and we have our private caches, and then we had our interconnect. Okay, so this is usually something like this that is happening, but it's much faster than going through the actual memory, because usually we have dedicated connection between the cores. It depends on the architecture, but sometimes this might be even not going to the interconnect and just directly if it's an on-chip system. It really depends on how we implement this, but it's something like that. And as I said, we can have both E and O, and we call this MOESI. And then, of course, the reason that you might have this is benefiting from O and E. These are orthogonal things, so you can have either of them, or both of them, or neither of them, okay? The last thing is adding a forwarder. You had a question? Oh, owner. Yeah, good. Yeah, so the question is, so first of all, yeah, it stands for owner. Good job. Sorry, I forgot this. So yeah, if we have something like SSO, means that all of them are sharing, but the difference is that this core has the dirty copy of this, right? So these two guys can safely invalidate themselves, but this one, if it wants to invalidate, it has to do the write back first, right? And the question is, oh, what will happen if we have SSO and then somebody wants to write, for example, this core wants to write, so this one has to go to M, this one has to go to I, and this one also has to go to I, okay? And then, as I said, typically when we are kind of writing on top of writing, we do write back to make sure that, all the writes are seen by the main memory. So this one write back, and then go to I, and these guys, this one goes to the M and then continues. Yeah.
So for the previous example, if we had, like, if we were reading from reading from R2 or having the instruction, would we have O for 2 states, or would it be O and then it drops to something else?
Here, give it, like, we have another R2?
Yeah, if we have like another R2, for example, or something else happens that doesn't involve core 1, then what would O do in the next stage? Would it keep being O, or?
Yeah, so the question is, like, if things happening here that doesn't concern core 1, what will happen? So you stay in your previous state always, unless something you need to change. So you don't change things unless you need to, okay? So you only go to from O, you can either go to I or you can go to M, right? You go to I only if you see someone wants to go to M, and you go to M if you want to write it. If you are the one who wants to write it, then you have to go to M, and everybody else has to invalidate themselves, right? Because now they have a stale copy, a wrong copy. Okay? All right, so the last thing is there are multiple cores in S. Everybody's in S. And now a new core wants to read it, okay? What should we do? For now, since we have S, so we have O and E, but none of them is doing the forwarding. So someone wants to read it. Who has to provide that data? Okay. If we only have S and O and E, so our current method is that if this core wants to read it, it has to go through the memory and read it. So at the next stage, it becomes S, 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 and S, okay? But obviously, this is an inefficient way of doing this because all of these cores have the data. Why one of them can forward this data to this core, right? But if all of them in S, which one is the one that has to do this forwarding, okay? To kind of fix this issue, we introduce another one called a forwarder, or F, which essentially we're saying that, okay, if I have a bunch of different cores, all of them in S, maybe if one of them becomes what we call an F state, a forwarder, then if another core wants to kind of switch to the S, this forwarder is the one that forwards this data, okay? And how do we actually do the forwarding? The forwarding can be actually combined with the E state. so that if everybody is in I, okay, the first one that goes to the E, okay, so everybody I, then, for example, if this core now wants to read, this one goes to the S, this E1, instead of going to the S, goes to the F, forward this data to the S, and then we move forward, okay? So the first core, the ones that the first time reads this data, becomes the forwarder, okay? Becomes the responsible for forwarding this data to any other core who wants to get a clean copy. Question? So the question is that if any of these writes, what will happen? So for example, if this core wants to write, this one goes to M, and this no longer has a valid copy, so this one goes to I, and so on and so forth, okay? And again, from here, we have a dirty copy, so F is only for clean copy, okay? So if someone else wants to read, this one goes to S, and this one goes to O, and this one stays in I, and again, O becomes the one that forwards the data. So we always either the forwarding becomes the responsibility of either an O state if you have a dirty copy, or the F state if you have the clean copy. Okay? Yeah. Yes, the comment was the only difference between F and O is that F is the one that has the clean copy. So if it invalidates, it doesn't need to write back data to the main memory. Versus if it's in O, if it's invalidated, it needs to write back to the memory. Yeah, exactly. O and F technically same thing. The only difference is that one is clean and the other one is dirty. By the way, another option for this problem that I said is that instead of having an F, we can have a round robin based system where essentially we say that, okay, any of the cores, we're gonna kind of like by choosing randomly, we're gonna ask one of them to intervene and forward. So many of the system doesn't really have an F state. What do they have is that in their snooping protocol, they just forward the data based on some random selection, okay? That's also possible, but in order to make things clean and nice, we usually have an F states in order to do that, okay? So kind of putting all together, we're gonna, at most, we're gonna have MOESIF, which essentially kind of like have something like this sequence. From I, we can go to E and then an F. From I, we can go to M and then an O, and then from I, we can go to the E and then an M, a silent M, okay? So this is kind of like the three sequences, and each one has its own benefits. The first one give you the forwarding capability. The second one saves a lot of write back and give you the forwarding capability of dirty data. And the last one saves you a lot of bandwidth in terms of silent updates, okay? Any questions? You can actually search for your own, for example, core model, see which of these cache coherence policy it use. Not all of them use MOESI. MOESI or MOSI, these are kind of like the most common ones. But you can actually check which one your system has. This is typically the information that is available in datasheets. Questions? All right, let me give you one last example. Let's do R1, W1, R1, I don't know, R2, then W3. So let's just start with I. You guys tell me what should we do next. For this one, let's see, we have all the states. What core one needs to do? E, right? Because this is exclusive one, everybody else I. And now we have W1. What should we do now? O or M? Okay, M. Why not O? You cannot go straight to the O because you're still the only one who has the exclusive access to this. So you don't go to O, you go to M. Okay, so you go M, I. And then if we do another read, what should we do? M, should we stay in M? Should we go to S or should we go to O? Stay in M, right? So you stay I. And then now core number 2 wants to read. What should we do? We go to O, right? O, forwarding happens here, S and I. And then if core number 3 wants to read, what should we do? So first of all, which state core number 3 should go to? M, yeah. What about 2? I. What about 1? I, and then of course the write back happens here, right? And then we continue. Okay. Any questions? Any doubts? Yeah. So kind of like things that we did was these 3 things, right? So in order to make MSI better, we kind of eliminate unnecessary broadcast that gives us a little bit more bandwidth. We eliminate extra non-necessary write-backs to the main memory, and then we also introduce some form of a cache-to-cache transfers using forwarding and using owners. And this is kind of like the state of the art in terms of cache coherence. Usually you don't need more than this. There are very special circumstances that you might need other things, but in most cases, as I said, MOESI F is the latest and greatest that you're gonna see in any processor. You're gonna have your homework stuff like that to play with this a little bit. So I'm gonna give you some examples to play with this MOESI IF things. So yeah, if you have further questions, you can always post it on campus for your ask the teams. You got a question? Say it again for first. Uh-huh. 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 So the question is, if one core is in O and there are some other cores in S, and for some reason internally that O needs to be evicted, what should we do? So when you're evicting that, it has to write back the data, right? And everybody else stays in S, and we just continue, right? Because now they have the clean copy, right? And now the question becomes, oh, if the new data comes, what should we do? Is there in a forwarding state or not? I mean, one optimization is that if somebody is in O and writebacks, maybe the snooping policy can assign an F to someone else, so someone can self-promote themselves. Or usually, as I said, if we don't have an F, we typically just randomly pick the one of them that is S and then ask them to forward the data. It's like very detailed. It's very specific on the microarchitecture. From one architecture to another, it might change. Okay. So there are a few kind of other notes about coherency that I want to talk about. The first one is what we call false sharing. So one thing that you need to understand is that caches, as we said multiple times, is everything happening at the block level. Okay, so even the coherency happens at the block level, not at the byte level. Okay. So if, for example, we want to invalidate something, we invalidate the entire block, right? If we want to promote something, we promote the entire block, and so on and so forth. As a result, there might be bytes within that block that has nothing to do with this sharing. Maybe you just share, like, let's say if you have a 4-byte block of 1, 2, 3, maybe I'm only sharing this byte between 2 cores, and these 3 guys are not really shared with anybody else. But as a result of this being invalidated, everything has to be invalidated. Okay. So we kind of we call this false sharing because these other bytes are kind of being sacrificed by the fact that one of the bytes needs to be invalidated. Okay. And this, as a result, might create extra misses because of this false sharing. So if I have 0, 1, 2, 3, and then because of 2, we need to invalidate this whole block. And next time I want to read line number 0, for example, and since this is a miss, we call this a coherence miss, okay? Because if I didn't share this, this would have stayed in my cache, and now because of this sharing of this other block, other byte in my block, I'm experiencing a miss, okay? So we call this a coherence miss, and this is kind of added to the 3 misses that we described: the compulsory, conflict, and capacity miss. We can have a fourth C miss, which is we call a coherency miss. Okay. Any questions about this? Okay. So instead of snooping, are there other options? And the answer to that is yes. Actually, snooping, the biggest issue with snooping is scalability. Because consider, for example, 4 cores. Every kind of transaction needs to be broadcasted. Everybody has to listen and so on. It's manageable for a small number of cores. But consider like if you have 1,000 cores, right? Every single transaction from each of these 1,000 cores needs to be broadcasted. So we're talking about a significantly busy network of these kind of communication and transaction. So we usually don't do snooping for very large systems. In most of our systems, including our laptops and mobile systems, since we have limited number of cores, we have like 4 or 8, snooping is a good option. But the option for very large systems, service scale systems, is what we call a directory-based cache coherence protocol. Essentially, what we do is that we keep a directory at the memory level for each address, and we kind of like in order to see who has this data, instead of everybody like kind of broadcasting things, we just go to that directory and check that directory. Okay. So for example, consider like a table like this, that let's say we have 4 different cores, and this is per line. So let's say this is like, for example, first set in the cache, and this is core number 1, 2, 3, and 4. Instead of like saying that, oh, I'm storing this per cache, I can say that, oh, okay, core number 1 has it, core number 2 maybe doesn't have it, core number 3 has it, core number 4 doesn't have it, something like that. Or we can even say that who has the dirty copy and so on and so forth. So the next time I want to do something, I can just go to the directory and check the status of that line, okay? So, and then if I store this kind of just giant table somewhere that I can kind of access it fast enough, then I don't need to broadcast anything. I don't need to snoop things. I always just talk to that directory. It's kind of like a centralized approach as opposed to this distributed approach that I described in the snooping scenario, okay? We always like, on a miss, we just go to the directory, update the directory, and then it's only one-time thing to every other cache, right? If something needs to be invalidated, the directory tell them that invalidate yourself or change it, so on and so forth, right? So it's a centralized unit. Everything that we know about each line is there. Anything that needs to be updated is there, and so on and so forth, okay? This is kind of like the basic idea of a directory-based system, okay? I don't give you more details about directory. If you're interested, you can definitely read more about it. Directory has its own problems as well, because of course the first problem is that now your directory becomes a bottleneck, because now think about like now 1,000 cores needs to go to one same directory, right? There are optimizations for it, as in like how do we access this in parallel and so on and so forth. Where do we store this and so on and so forth. That if you're interested, you can definitely just Google directory-based cache coherence, and you'll see a nice Wikipedia article about it. But if you also take an advanced computer architecture course, we will discuss this in more details. Okay? Questions? So that's it for our coherency protocols. As I said, the coherency is caused by the fact that we are sharing lines, and because we are having this private cache lines in our systems. Okay, if you don't have either of them, then we are good to go. But we have to have both of them, so we have to fix this coherency protocols. Any final questions about coherency before we move on to consistency issues? All right. So remember, recall that, we talked about the second issue, which was the consistency issue. So the issue of consistency is something like this. that, by the way, this syntax is not correct, so apologize. But what I'm trying to show here is that one core tries to load Z, the other core wants to try to write to Z. One core is trying to store to Y, and the other core wants to load to Y, load from Y, okay? And assuming that this values of x2 and this value of 100 and 200 is different than the initial values, what will happen is that we can have very different outputs for x1 and x2 depending on the timing of this execution, okay? So first of all, these two cores are running independently. They don't synchronize to each other. So things can kind of interleave, right? So we might run this one first, and then this one, and then maybe this one, and then maybe this one. That's one possibility. The other possibility is, for example, let's do this one, this one, this one, and this one. Sorry, 3 and then 4. And then we can also have the other way around. So this one might first run, and then this one, and then this one, and then this one. And so we have kind of all of these different possibilities. And then in addition to all of these, we also have out of order execution possibility where things within each core can also be kind of moved around. If we have LSQs, this is not possible, but if we don't have LSQs, this is also possible that, you know, this might, since this is independent from this one, we can actually run this before this one, right? And if the other core doesn't see the correct ordering, that could cause even further issues in our systems, okay? As a result, it's kind of like all 4 possible values of x1 and x2 is possible if we don't put any sort of control on this system, okay? So what I want to talk about in the rest of this lecture is, first of all, what are these problems and what do we do in order to fix this? An important thing about consistency is that unlike these other things that completely solved by hardware, consistency is actually a problem that also involves software, okay? So the developer needs to know about this and needs to do things in order to fix this. So it's not something that hardware can completely fix. It's because of the nature of concurrency between cores, software developer needs to actually intervene here. So everything that we discussed so far was completely oblivious to the software, but this last thing that we're going to discuss in this class about consistency is actually kind of co-design between hardware and software. So just one thing that I want to pay I want you to pay attention to. Okay. So of course you have these questions of, oh, what happens to the raw data hazard? What happens to the correctness? And what happens to the LSQs? So first of all, neither of these cases has raw data hazards, okay? So for example, if you look at this example, there is no raw data hazard between this one and this one. These are completely separate addresses, okay? So we're not introducing correctness issue to this processor. Everything that we had and discussed before stays the same. We are making sure that we are not creating new issues by reordering. This is just the nature of the way that we are writing this program. This is just bad program that we are writing. And as you will see, if you actually do some parallel programming, you'll see that this is very possible. In many cases, you might have scenarios like this, that you update some value locally in one core, but the other core is actually using that value. And that's a very, very possible thing in many of parallel programming systems, okay? So we are not introducing any raw data hazards. We're not introducing any correctness issues. And LSQs can still be there. My point is, if we don't have LSQs, this might be an issue. And also another thing that might be possible is that the compiler might reorder things. So the things that we write in the C or high-level language program is not exactly what it will translated into the instruction. So we might think that this happens before this, but the compiler actually sees that, oh, this one is independent from each other. Let's move this below or above this previous instruction, okay? So as a result, we're going to see all these problems, okay? So it's kind of like this slide to tell you that the reason that we are seeing this is not because we are not doing what we were doing. Even in the presence of all those things that we were doing before, we're still going to have these problems, okay? So one thing I want to talk about is that there is like one thing that people very, very quickly confuse is the difference between coherency and consistency. And to some people, it seems that we actually fix this issue in coherency, but that's not the case. The reason for this is that consistency is talking about different addresses, okay? We are talking about different ordering for different addresses, okay? So things that we did for raw data hazard and for coherency was for the same address. Remember, in our coherency, we always talk about only one address, and that was Z, okay? For consistency, we are talking about two separate addresses. The only problem that we are seeing is the ordering of these things are changing, okay? So that's something to understand, that this is a more issue of the timing. It's not an issue of the address, okay? So again, to kind of summarize, coherency versus consistency is that consistency is the issue of timing between different addresses. Coherency is the issue of timing between the same addresses. Okay, so hopefully that cleared this up. So let's actually now talk about fixes and see what we are doing at the hardware level first, and then I'm going to talk about what we should do at the software level with the help of hardware, of course, in order to fix this issue. Okay. So first of all, as I said, this will eventually becomes the programmer's job. Okay, as I said, this is slightly different than anything else. For example, when we were talking about caches, when we were talking about branch prediction, about all those things, we said that, oh, there are problems, but we fix that problems in hardware. The programmer doesn't even know what is happening. Doesn't even know that we did a misprediction and we flushed and we come back and then we reran. Doesn't even know that we reorder things, right? But on the consistency problem, the programmer does know and has to know and has to do something about it. Okay, so that's something I want to point out. And as I said, we need to fix this basically reordering problem. Okay. So in order to fix this, the very first step that we need to do is what we call a memory model, okay? So basically, in order to fix this problem, especially at the higher level programmer level, the programmer needs to know what are the possible reordering in this particular hardware that I'm going to run this program for, okay? And we call this a memory model, okay? A formal definition of memory model is that the interaction between threads and the shared memory, or in other words, what are the possible values or what are the possible reorderings of actions? For example, if I know that there is an LSQ that can reorder writes for me versus if there is no LSQ or writes will not be reordered, that's completely two separate stories, okay? So as a result, the programmer needs to know what is the memory model, okay? I'm going to describe some of the memory models. So the first one is what we call a sequential consistency, and then we're going to talk about total store order, and then we're going to talk about relaxed or released consistencies. But what is important is that for the targeted hardware that we want to use, we need to know the memory model. For example, ARM using some form of relaxed consistency memory model, but x86 Intel's using some form of total store order memory model, okay? As a result, if you're writing a parallel program for ARM, things that you should consider and assume is different, slightly different than what when you're writing for x86, okay? And again, this is another difference when we are writing programs. Again, so far we never discussed the difference between things, and we said that ISA kind of abstraction layers kind of figure these things out for us. But when it comes to consistency, it no longer works. So we need to actually know which hardware is there for us. Okay? Any questions so far? Cool. So the basic one is kind of like the first model, the most restrictive model is what we call a sequential consistency model. In sequential consistency, basically everything happens in order. So sequential consistency gives you these three rules. The first one is each process within their own system, they see the loads and store in program order. Process sees the others' loads and store in program order. And then all the processors see the same global ordering, okay? So everybody sees their own ones in program order, everybody else in program order, and as a result, everybody together sees the exact same ordering. In other words, sequential consistency basically telling you that there is no sort of concurrency. Everything's going to be kind of like linear, all right? And sequential consistency, or SC, is great because this is exactly what you expect when you're writing the program. It makes things very, very simple because you know exactly that, okay, this is how I write this program. This is going to be exactly how it's going to be implemented in hardware, okay? You can reason about your system very, very simple. The biggest problem with the consistency is that consistency essentially kind of make your system indistinguishable from a uniprocessor. And the results, all of those optimizations of reordering things and doing things out of order, we put them in the trash, okay? So of course it's great, but it's not kind of feasible. Not many systems is actually using sequential consistency because it's too restrictive for our systems, okay? So what do we do instead? In order to understand what do we do instead, we have to think about what are the possible memory reorderings, okay? So we have 4 type of memory operations. Sequential consistency basically telling you that all of these things should happen exactly as it says. So write should happen write should happen before subsequent reads. Read should happen before subsequent read. Read should happen before subsequent writes. And of course, write should happen before subsequent writes. Sequential consistency basically telling you that all these 4 things should happen. There is no reordering possible in any of them, okay? But of course, we want to do, and then again, these are separate addresses, okay? One more time. These are separate addresses, not the same. For the same addresses, we had the raw data hazards. We already fixed that, okay? This is for address Z and address Y. So sequential consistency even say that you cannot do Z before Y, even if they are different addresses, okay? So it's something that you want to pay attention. So what we should do is, instead of sequential consistency, it's something that's a little bit more relaxed, okay? We want to be able to reorder some of the things. Maybe at least read before read seems to be something that we should be able to do, right? So this is the introduction of what we call weaker models or relaxed models, okay? So when we're saying a weak model or relaxed model, what are we relaxing? We are relaxing sequential consistency to something else, okay? And basically what we are relaxing is that some or all of these requirements, okay? So when I'm telling you, for example, that ARM core is using relaxed consistency, it means that some of these reordering is possible in ARM under some special circumstances, okay? And then the reason that we call it weaker, because this is, of course, the strongest possible consistency model, because we're not allowing any sort of reordering. Anything other than this becomes weaker, okay? So we call it weak or relaxed consistency, okay? So as I said, some of these might be violated using relaxed models. The first one that we're going to talk about, and this is actually the ones that x86 use, it's the most common one, is what we call a total store order, okay, or TSO model, okay? The TSO model is actually, it's not something new. It's something that we already discussed, okay? Remember we talked about LSQs, and I told you that, if I write things, it's going to kind of store here, and then based on the retirements, we're going to actually put it into the shared memory. This is based on this TSO model. The reason that we didn't talk about it at that time, but TSO is nothing new. It's basically what we've seen before. It's a load store queue system that's reorder your writes and make sure that your writes is actually happening in program order. How do we do that? If you remember back in the day, we had our ROBs, and we had the retirements, and we had the head of ROB, and we said that things go inside the ROB but won't be retired until we reach to the head of the ROB, right? So this is actually by storing these things in our LSQs, we are guaranteeing that only we write things from LSQ to the main memory only if things are retired in order, right? So the idea of the TSO model is that every core needs to have this store model. I mean, TSO is only telling you that store needs to be in order. LSQ is kind of a more generic term that your load and stores become in order, right? So that's something to remember, that TSO doesn't need to be loads, it's only stores. So if I only make sure that my stores happening in order, then I have the TSO memory model. Okay? Questions? And then the big thing about the TSO model is that, you know, the reads by other processes cannot return value of A until A is actually written to and observed by all the other cores. Okay. Again, this is kind of like an artifact of having this store orders, that if somebody wants to read that particular value, we have to make sure that this value is being forwarded by the other store order. And again, this is the part that that we kind of fix this by making sure that the retirement's happening in order. Okay. Let me give you this examples, and then we can have a quick break. So let's say, for example, how TSO could help with us in this particular example. Let's say we have two cores, okay, or two threads, thread 1 and thread 2. Let's say in thread 1 we have these two instructions. I'm using a kind of like arbitrary. I'm not using a particular ISA. I'm just using some form of a pseudocode. So for example, let's say I want to store number 1 to A, and I want to also store number 1 to flag, okay? And these are two separate variables, okay? And let's say on thread 2, we have this kind of code. This is kind of a loop that we have an if condition on the flag. If flag stays 0, we kind of what we call a kind of a spinning. We kind of looping until the flag becomes 1. Once the flag becomes 1, then we load the value A, okay? And let's say initially these two values are zeros and zeros, okay? So if you think about this, is if things happens in order, okay, the way that we expect it to be, we are expecting that we first write 1 to A, so A is 1, and then we write flag equal to 1 here, okay? As a result, on this part, until flag become 1, nothing will happen to A. So at this point, at the end of this program, it is guaranteed that A should be equal to 1, okay? This is kind of what we intend to achieve as a program, right? We intend to achieve A equal to 1 at the end of this program. But if it didn't have something like TSO, that's if the writes can kind of be reordered, what could have happened is that these two things could have been reordered. So if flag happens before writing 1 to A, if these two independent writes can be reordered in a particular core. And by the way, again, these are independent, and thread number 1 has no idea that this is going to be used in another core, okay? So it's totally possible that these things become reordered if we don't have any sort of checks, okay? So if these things reorder, if flag happens first and A happens next, then we're going to have some form of a race condition here, right? So if flags becomes equal to 1 and A has not been updated to 1, it might be a chance that this happens very quickly. So the moment that the flag becomes 1, we go inside the loop and read the value, and value at this point is still A equal to 0. So instead of reading A equal to 1, we might actually read A equal to 0, because again, this is a race condition. The time that we are writing 1 to flag and the time that we are writing 1 to A, this process might be very slow compared to this process, okay? And as a result, we might get a wrong value for A. A could be either 1 or 0, depending on how we're doing this, okay? So the way that TS are going to help us is that if we are guaranteeing that this write happens in order, then the possibility of flag happening before A is not a viable option. We only see this so the other core only see this when these things are actually retired in order. As a result, we are guaranteeing that A is always equal to 1. Does that make sense? Any questions? So this is how, by making sure that the writes is happening in order, the programmer can reason about this. So if you want to write this program, you can say that, okay, I know that my system has a TSO model, so I can actually do this. But if you know that, for example, your model doesn't support TSO, then you shouldn't write a code like this, okay? You should find another way of writing this. And in fact, many systems doesn't have TSO. As a result, you have to actually figure out something else. Yeah. Yeah, the question is, the flag is kind of a lock. Yes, we're actually going to talk about locks. It's a kind of a mutual exclusion here. Yeah. Any other questions? Cool. So we can actually also compare TSO with SC. Let's have a quick break. We'll come back and we talk about this. Okay, let's continue. Okay, so let's continue, guys. So let's revisit this example here, and then let's see what is changing between TSO and SC. I want to kind of point out two things here. So first of all, as you will see, is that either the SC or TSO not gonna help you fixing all your problems. Memory models is just there to give you the possible options. Okay, so as you will see, for example, in this system, even if you have SC or TSO, you're still gonna have the problem at where let me see. Let me just close this. Okay, so we're gonna still have the same problem that we have before, even with SC, because what SC gives you is that it tells you that this cannot happen before this. Okay, sequential consistency basically telling you that we can only do this first and then do this next. Okay, and then we can only do this first and then do this next. Okay, but it doesn't help you between them. Okay, so you can have either 1, 2, 3, 4, or you can have 1, 2, 3, 4, and then again the other way around, like these two first and then like interleave. The only thing that is not possible anymore is you cannot have this first and then this next. Sequential consistency doesn't allow you to do that. Okay, but between the synchronization between the cores, neither sequential consistency nor TSO are gonna do anything about them. Okay, so you still have that issue, and as I said, this is where the programmers has to intervene. Okay, but the difference, of course, between TSO and SC is that, as I said before, SC only makes sure that your stores are happening in order. So technically in TSO, you still might have a scenario where this happens first and this happens next. Okay, by definition, this is still a possible scenario because TSO just give you ordering for your stores, doesn't do anything for your load and stores. As I said, a more comprehensive solution is if you have an LSQ, and then in that case you have both loads and stores, and in that case this is not possible. But by definition, if I give you this and say that what is the possible outcome in TSO, you technically can have all the possible outcomes is still in TSO. Does that make sense? Cool. All right, so we kind of allow reordering of stores per core. This can help us significantly improve the performance. But there is still the synchronization problem between different cores, and that's not something that either SC or TSO are going to help you to solve. Okay. In addition to SC and TSO, there's a whole bunch of other weak consistency models. Basically, each one kind of lets you to kind of reorder things in particular cases. Okay. The difference between them is the performance versus complexity. Of course, in one end, you want to be able to reorder everything, right? If you can reorder everything, that's the maximum possible performance that you can get from your systems. But the downside of reordering everything is that it makes it crazy complex for the programmer to understand what should happen in the system. Okay, and as a result, the programmer needs to change things. It might be very buggy code, etc., etc. That kind of like defeat the purpose of getting performance. If you cannot really write a program that can benefit from that performance gain, what's the point? Okay, that's why we kind of like most of these systems have something in between. Some things can be reordered, some other things cannot be reordered. And it's only important for you to know which memory model we are using, and based on that, writing our programs. We're going to talk about another one called release consistency, but before that, I want to talk about some other things. But we're going to get into another one that's called release consistency. Okay, but essentially TSO is the ones that most of their systems, including most of the x86 systems, is used. It basically says that the only thing that I cannot do is I cannot reorder writes between them. Okay, everything else possible. Okay. All right, so now that we know that the memory model is given, now that the question becomes, how should I write my program in order to avoid any of these? In order to do that, the good news is that the hardware gives you some tools, okay? So we're going to talk about things such as locks and fences and semaphores and all those things. There's some synchronization tools so that you can kind of reason about how the cores in terms of like, respective to each other, how do we kind of like make sure that the timings are kind of right, okay? So I'm going to explain those kind of tools at the high level. I'm not going to explain the actual hardware implementation. We might actually do a little bit of this at the end, but then we're going to show how this can help us in order to achieve what we want to achieve, okay? And again, if you want to know more about weak consistency, that's another thing that you can just search and read a little bit more about different, like, for example, the ARM consistency model is an interesting one that you want to learn a little bit more about. I specifically don't go through it because it's very advanced topic, so we don't have time for it. All right, so let's see how we can write a good program that doesn't have memory consistency issue. Of course, the first thing that we can do is we can say that, okay, let's actually write something that is race-free, which means that we avoid scenarios where based on which one is faster, we can have different outcome. If I can write some programs that doesn't matter which ordering I see, I still always see the same outcome, that's the best scenario, right? Because I don't care if you want to reorder it. If you don't want reorder, don't reorder it. I wrote my program such that values are completely independent from each other, so that it doesn't matter which reordering is possible. The reality is that you cannot really do this in most cases because there are many scenarios that because you're writing a parallel program, many of your variables are being shared among different cores, okay? And as a result, you of course want to read this value, write to this value, and do all those logics on this value. So you cannot say that, oh, okay, I kind of take a copy and then the other one takes a copy, because if you do, then there's no concurrency, and if there is no concurrency, you're not going to get any performance benefit in your system, right? So it's kind of like we are having this kind of circular problem that if we share, we're going to have problems. If we don't share, we're not going to get performance, okay? So writing race-free program sounds good, and you should do it in most cases if you can, but the reality is that in many systems, you cannot do this just because of the nature of the program that you're trying to write, okay? So what should we do is the first thing that we can do is that we can let hardware take care of everything. Same way that we did before. And we can have mechanisms for keeping track of each write, keeping track of each read. Maybe we can put some flags. We can tell hardware when the things needs to happen and so on and so forth. In fact, there has been attempts for this, and there are systems that can do this for us. The short answer to this, whether it's just a good idea or not, is that it's very, very costly. It's significantly costlier than having, like, coherence policies. And that's why in most cases we don't really do this. We're just adding some form of kind of primitives that I'm going to describe in the next few slides, and use this primitives, use this arsenal of tools to the software programmer and say that, okay, use these things in your program, and then if you use them correctly, then hopefully your program will be running correctly. Okay, so this is kind of the right approach, this kind of balanced approach. Instead of doing everything as software by writing a race-free program or forcing this hardware to keep track of things, we kind of like find a middle ground here. Okay, so what are those things? So the idea here is basically using some form of synchronization. We need to synchronize different part of my program that runs on different cores. And if I use the synchronization correctly, then I can reason about my system. So for example, saying that, okay, if this is my code in core number 1 and this is my code in core number 2, maybe I can say that, okay, I want this order, like within this core, I want to kind of do this. And then once this part is finished, I want to run this part. So if I kind of can synchronize here and here, saying that, okay, I need some way that guarantees that this runs first and then this runs, then I can write good program. Okay, so this is basically the idea of what we call synchronization, that basically we force the system to follow some ordering that you want them to do. Okay, so what are those synchronization? There are two major models for synchronization. Okay, the first one is what we call a producer-consumer model, which one core produce something and the other core kind of use it, or one part of the program use it and the other part of the program take advantage of that. The other one is what we call a mutual exclusion, which means that essentially if there are two things that wants to do the same thing, all we need to do is making sure that at any given point, only one of them can do this. And once that finish, the other will see the updated value of that. Okay, so the first one is kind of some form of serialization. This is basically the examples that I gave you. This is kind of a producer-consumer model, which I say that, okay, this process goes first, kind of generate and produce the results. And at this point, this process should go next and use this results. Okay, the other alternative is that if I have these two codes, I say that, okay, both of you wants to update some value. Maybe I create this kind of mechanism that say either you are able to do this first, or you are able to do this first. Whoever does it first has to update the value. Then you go next. So this one goes first and this one goes next. And the only difference is that once this one finishes, this one has to see the updated value. Otherwise, there is no point. Okay. So the difference between these two is that the first one, what we call a producer-consumer model. The second one we call a mutual exclusiveness. You can use either or. In some cases, you need to do both in order to achieve what you want to achieve. And for both of them, we're going to introduce some tools in order to achieve what you want to achieve at the hardware level. Okay? Any questions so far? All right. So the first thing I want to introduce is the notion of fences. Okay. So there is this thing called fence, which is actually literally an instruction. And what it does is that it enforces all the memory operations before the fence to finish, before doing anything below it. Okay. So essentially what fence does is that it serializes things within each core. Again, fences does not do any sort of synchronization in between the cores. But the good thing about fence is that if I have a bunch of, memory instruction here and have a bunch of others here, what I can do is that I can say that, oh, you guys reorder as much as you like, but then I'm going to add this fence here. Okay. And then what this fence does is that it guarantees that anything that happens here only happens when all of these things are finishes. Okay. So the fences give you this kind of temporary capability that you know for sure that if I reach to this point in my program, everything above it has already finished. Okay, so it serialized things before it, and then you can still reorder things on the top part, but once we reach to the fence, once the fence is finished, we are guaranteeing that everything done at that point. Okay, and this is very, very handy thing because fence can be kind of helping you to kind of make sure that things below it doesn't kind of blow over and move over the fence. So you cannot move things from here to here, obviously, right? The fence is literally a fence. Okay, it doesn't move things between the two sides of the fence. Okay. But as I said, this is just within one core, not between the cores. So fence, if I have one fence and the other fence, these two don't talk to each other and they don't mean anything, okay? So if I have a fence in core 1 and another fence in core 2, it doesn't mean that when I finish both fences, they're at the same position. No, this is not the same thing, okay? So what should we do between the cores? Between the cores, we are kind of using this concept called semaphores, okay? Which is we also call it barriers. So this is where kind of terminology different from one book to another and one class to another. But basically, barriers is these things that kind of synchronize the time between multiple cores, okay? So we usually have barriers, some form of barriers that has some form of a number. So that, for example, if I have one core that's kind of running things here, and then I have another core that's running things here, if I have, for example, a barrier here and a barrier here, what will happen is that this means that at this point, we are guaranteeing that everything here and everything here has finished, okay? So this instruction here cannot execute until this last instruction from this other core finishes, okay? This is a barrier. This is kind of like a synchronization points that, think about it, that you're kind of running on the road with your friend. You kind of say, okay, when I reach this kind of stop sign, I'm going to wait until you arrive. I'm not going to move past this stop sign until you reach to me, okay? If you don't, I'm going to wait there. So barriers basically means that one of the cores has to kind of sit idle until the other cores catch up. Okay, of course, it introduces extra performance overhead, but it's very, very useful to make sure that things is kind of like, in the same time. All right. So so we typically typically use this, and semaphores usually it's a software concept. You don't really need to implement this in hardware. Fences is actually implemented in hardware. So there is literally an instruction called fence. And we usually have like a read fence and write fence and read write fence. So we have for example, x86, we have things like L fence and S fence and so on. Sorry, this in RISC-V we have this, which means that L fence means that I only make sure that all the loads finishes before we reach to the fence. S fence means that we make sure that all the stores finishes, and I think it's A fence. I don't remember honestly. We have to check it, but I think A is that all the instruction, all loads and stores needs to finish that we reach to that point. Okay, so fence is actually a hardware concept. It's literally implemented in hardware, but semaphores and barriers typically is something that the operating system takes care of. Okay, we usually implement it in software. And then implementation is not that hard, right? You just need to make sure that the PC that you think it has to reach is there. If it reaches to that point, you need to create some form of an interrupt or some form of an exception or a trap. Make sure that the process stays in that trap until the other process catch up, right? And I don't, as I said, I don't go through the actual implementation because this is more of an operating system concept. Okay, so how do we actually help? How does this help? Remember this example that I gave you? If I have some form of semaphores or kind of a barrier here, if I have something like this, that I put a barrier here and I put a barrier here, then this will guarantee that these two instructions runs first, and then these two instructions are going to run next. Okay, so in this particular case, if Z was so this one is going to read z, and then initially z was equal to 0. So x1 would be equal to 0. Then we're going to write 100 to y, and then we're going to load this. So x3 going to be 100, and then we're going to write 200 to 0. That doesn't matter. So after running this, it's kind of guaranteed that we're going to see this. One specific nuance that I want you to pay attention to is that I didn't talk about the memory model here. So remember, if I have TSO versus SC versus something else, things within the core might be still reorder. So your barrier or your semaphores is going to just synchronize things in between. Still within the cores, you might have reordering. In this particular case, it doesn't matter, but there might be some other things that, reordering within might create some issues. So don't confuse the memory model and the possibility of reordering with the synchronization capabilities that we introduced, including fences and barriers and so on. Okay, two separate things. Together, they will guarantee that your system works, but you have to consider both of them in order to make sure that your program works. Okay, any questions?
So just to clarify, barriers are kind of also, so barriers are across processors, right? But does that also mean that does that also mean that it's basically a fence within the processor itself?
So good question. The question is a barrier also works as a fence or not? Yeah, kind of it does, because what barrier does is that it says that this thing cannot happen before this. So yeah, so barriers, in other words, is also kind of creating serialization between the instruction before and after the barrier. Basically, what barrier guarantees is that things before this as finishes and things after this cannot start. So in other words, this is some form of offense. Good point. An interesting thing is that you can have multiple barriers, and you can have barriers between different cores. So, for example, I can have an instruction like this might be my core 1, this might be my core 2, and this might be my core 3. Okay. So what I can have is that I can have, like, let's say a barrier here. I call it B1, for example, between here and here. I might have another barrier, for example, I don't know, here, call it B2 between here and maybe here. Okay. And these are two independent things. Okay. This one says that this part cannot start before this part. This one says that this part cannot start before this part. Okay. And you might have multiple barriers between all the cores that you have, or between any pair of cores that you have. So for example, you can also have maybe another barrier that kind of like say, oh, everybody has to reach to this point. Okay. So as I said, these are kind of like depending on the implementation of your operating system, but typically operating systems give you ability to have multiple barriers across cores, between all of them, and so on and so forth. Usually the terminology that we use is some form of this, like B1, B1, B2, B2, to kind of indicate that these two are the same barriers and these two are different. So B1 is different than B2, but B2 here and B2 here is the same barrier. Yeah.
So a question about, so these barriers for synchronization, right? Is there any way, so for example, if core 1 finishes a lot faster than core 2, but if the barrier is stopping something that can just be left there, and then is there anything allowing core 1 to just continue working on other things, or just not?
Yeah, that's a good question. So for example, if core 1's reach to this barrier and core number 2, which needs to be reached, is like way behind, what happens here? We just idle, make the core number 1 idle. So you want to write your codes. So this is more of, again, goes back to the programmer and writing a good program, that you want to put your barriers that kind of like at the same time. Otherwise, it's kind of become like this. So again, you won't get performance out of your system. Very similar to the pipeline stages. You want all of your kind of pipelines to be at the same time. Here, you also want to do this. Part of it's inevitable, because interesting thing is that when barriers are mixed with some other things that we learned about in the course. So for example, assume that, for example, in this core here, we might have a misprediction or a cache miss, right? we need to pay a lot of cycles, wait for a lot of cycles for this to finishes, but this one doesn't experience any cache miss, okay? So there will be a huge time difference between these two, and this is the price that we need to pay. But again, good writing codes is very important here, because we need to make sure that if they have similar cache pattern activities, maybe they experience both a miss or a hit, so that we don't kind of pay this penalty. All right, so this was kind of like a consumer producer model kind of thing, because we are introducing this kind of, oh, wait until I finishes and then you can go. An alternative, as I said, is mutual exclusiveness, okay? For mutual exclusiveness, we basically define this as for a given part of a code, only one particular core can access this, okay? So if there is a shared region or shared value, only one of the cores that has access to this can update this. Others can only read the updated value once that core is finishes, okay? How do we do this? We introduce this idea of mutexes or locks, okay? So lock is, think about this as, for now, as just function, that what it does is that, you know, you have, let's say you have this code and this code, and both of them wants to update these values, okay? So what we usually do is that we introduce this acquiring the lock and releasing the lock here and here. I'm not showing it here because here I want to say that, for example, this core is getting the lock. So if there is something that you're not really sure about, that, you know, things might happen in parallel, what you can do is that if you add lock here, you acquire it and then you release it, what will happen is that this kind of mutex or this kind of exclusiveness will guarantee that either this part will happen or this part. There cannot be interleaving between them, okay? Because you either have the lock or you don't have the lock. If you don't have the lock, you cannot enter. If you do have the lock, then you can enter, okay? But the difference is that you cannot guarantee who gets the lock, okay? So if this core and this core both wants to get the lock at the same time, that is a random activity, a random event. Either this can go first or this can go first. But the important thing is that with locks, then we're not going to have interleaving like this. This cannot happen, okay? So you will either have this or we have this. Okay, so that's the difference between mutual exclusiveness and not having mutual exclusiveness. Okay, and then the reason that we have a release lock is that if you don't release the lock, then we're going to have problem with other cores, because other cores are going to stay in what we call a deadlock, which means that we're waiting for a lock that never comes. Okay, so it's very, very important that if you get the lock, if you acquire the lock, you release it at some point so others can also use it. Because remember, this is still a parallel programming, program. It's a parallel program. So if other cores cannot really move forward, there is no point of writing a parallel program. Okay. So locking is important, and you have to make sure that you release and acquire the lock. And based on this lock, we can actually have what we call the release consistency model, as I said before. So the release consistency model is basically this, is that it's a consistency model that we say that it is guaranteed that all the writes and read are executed and visible to other cores once we release the lock, okay? So in this case here, if this system has a release consistency, at this point that we're releasing the lock, this core will guarantee to see that this one and this one is done, okay? We call this a release consistency model, that every activity within that kind of mutex is observable by every other core, okay? If it didn't have release consistency, then this wouldn't work, right? Because still, we might get the lock, but might be this store might not be finishes yet. If the store has not been finished yet, then again, this might read an old value, and we're going to have the same consistency issue that we have. But we release consistency, we're going to guarantee that if we release the lock, we finish all the operations within that region. Okay. And the important things about release consistency is that basically we're saying that other than this kind of releasing the lock, any sort of ordering is happening within the lock and outside the lock, okay? So release consistency is actually very, very efficient in terms of performance because you're basically allowing any sort of reordering, but you're just saying that, okay, if I have the lock, I can do things, and when I release it, I need to make sure that things are being written, okay? So that's the difference between TSO or release and sequential consistency, okay? How do we implement an acquire and release? So we have this thing here. There are multiple different implementations. One that I'm showing here is kind of, like, first of all, I'm showing the software implementation. I'm not talking about hardware implementation yet. So acquiring lock is something like this, okay? So the acquiring lock is it's a function that takes locks as an input and probably some form of busy waiting. So it waits for the lock to become non-zero. When lock is 1 means that it's available. And the moments that is available, we want to write to it to make sure that we are the only one who gets the lock, and then we return, right? So this is some form of implementation of acquiring the lock, okay? We wait until the lock becomes available, becomes 1. The moment that it becomes 1, we can write to it, and then we get the lock by having that, okay? The assembly version of this looks something like this, okay? So we kind of load array x0 array, okay? And this is kind of like the return address. Then we say that, okay, if branch not equal 0, we just keep doing this, okay? And then what I'm assuming here is that the memory address of x1, so basically this is equivalent of reading the lock, okay? It's equivalent of this part. All right. So we kind of keep checking that x1 address and reading this value. We're saying that if this value is equal to 0, then keep reading this. If it's not, we're going to continue. What we do, we need to write 1 to that address, and we need to basically store that value to that address, okay? So this is just writing 1 and then storing that value, okay? So this is basically equivalent of this part of the code, right? Any questions from this assembly code? All right. And then how do we release the lock? Release the lock is very simple. We get the lock, we write 0 to it, right? Which is equivalent to some form of store to the address of the lock, right? So very simple. But let's actually look into kind of core number 1 acquiring the lock and core number 2 acquiring the lock and see if there is any problem here. Do you see any problem? And can anybody say that both cores wants to acquire the lock at the same time? What do you think might happen here? Yeah. Exactly. So with interleaving, we might actually, both of them thinks that they have the lock, right? So for example, this one first goes in and see that, oops, lock is actually 1. It doesn't do this. It continues doing this. And at this point, this core also might actually read the value and check this and see that, oh, the lock is still 1. So it goes in. And then this one will write 1. This one will write 1. But both of them thinks that they have the lock. So there is nothing mutual exclusiveness here. There's no exclusivity here because we are still in interleaving, okay? So this is obviously is not the right way of implementing this. There needs to be some form of kind of exclusivity or some form of exclusiveness within acquiring the lock, okay? How do we achieve that? We achieve that by using what we call atomic instructions, okay? Atomic instruction means that basically the atomic primitive in hardware is by definition is this hardware primitive that tells you that sequence of instructions are running in order without interruption, okay? So basically, if I have these kind of instructions here and this kind of instruction here, if I say that this is running in atomic fashion, it means that all of these things happen, first of all, in order, which means that there's no reordering between them. And it also means that nobody else is doing anything while I'm doing this. So no interruption by other cores, okay? So this atomic instruction is actually very helpful because if I can run this in atomic fashion, then I'm kind of guaranteed that there's not going to be any sort of interleaving, okay? The only thing about atomic is that you don't need all of these to be atomic. Maybe just part of it needs to be atomic. The part that you read and write needs to be atomic, right? So what we do usually is this idea of what we call test and set, or generally like load and store conditional, okay? Load, link, and store conditional. So here's what we're going to do. So here's the kind of like the correct way of acquiring a lock, okay? We're going to have this function called test and set, or you can just call it acquiring the lock. And here's what we're going to do. Instead of reading and writing, we're going to implement this special instruction called swap. And this swap is an atomic swap, which what it does is that it's swapping one with the value that it reads, okay? So what it does is that it basically, this x is if this x is my lock, what I'm going to do is that I'm going to read the value and I'm going to write 1 to it. And this process is atomic, which means that I am the only one who can do this, okay? So what will happen in this case, if I go back to here, basically what will happen is, actually, let me go back to here. If I do this, instead of like doing this, what will happen is that this process here, I'm replacing it with a swap, okay? Which means that I read the lock, either the lock is 0 or 1, okay? If the lock is 0, right, it means that it's still busy, okay? Sorry, if the lock is 1, it means that it's still busy, right? If it's still busy, I'm going to swap it with 1. So I read 1 and write 1 to it, nothing happens. But if the lock is 0, it means that it's available for me to read. As a result, so I'm going to read it and I'm going to immediately write 1 to it. And in this case, if both of these cores doing swap at the same time, okay, only one of them can do it and the other one cannot, because this is guaranteed in hardware that this is atomic. So if this one does it, this one cannot do it, okay? And if this one does it and the lock is available, immediately going to write 1 to it. So this one, the next time that this one reads it, it's not going to be able to read it correctly, right? It's going to read a 1, right? It's not going to read 0. So this one will read 0. This one will read 1. One of them gets the lock, and boom, very good. Okay? This is what we call test and set. Basically, we test and we set, right? So we test that whether the value is equal to 0 or 1, and then we set this value, and then we return this. And this is basically you're acquiring the lock, okay? And the beauty of this is that only this part needs to be atomic. Basically, only this instruction needs to be atomic, and that's all you need in order to achieve the lock. There is also other version of test and set. There's called compare and swap and fetch and add. I'm not going to talk about those, but there are other variants of test and set. Essentially, all of them boils down into some form of atomic instruction that you have in order to make sure that your system is not doing some sort of interleaving between your cores. Okay? Any questions? Cool. So how do we actually implement this in hardware? How do we actually implement swap in hardware? For RISC-V, we have this special instruction called LL, or load, link, and store conditional. So the way this works is we're going to load this value, the value of x1 to x2, and then we're going to store this, and then in between I need to kind of write 1 and store it. And what we're going to do is that this load, link, and store conditional is going to have this particular scenario that if I do this load link, not only I load this value to this register, I also kind of monitor or flag this line of memory. If somebody writes to this line during this process between load link and store conditional, if somebody else writes something to this, which means the other core, for example, wants to acquire the lock, this store conditional will fail, okay? Which means that we're gonna get we're gonna execute this branch not zero value and then go back to the label, okay? So at this point, this is store conditional, we're gonna check that during this process of reading and writing, has somebody else write something to this line or not? If they do, then we're gonna return 0, and then we're gonna jump back to the label and repeat this process, okay? So we're gonna keep doing this until we make sure that nobody else has checked that value. And this is why this is kind of an atomic. In reality, it's not atomic, which means that everybody else can still write to this, but we are guaranteeing with load link and store conditional that if I read and then write, if somebody else has write to this, it will fail. If nobody else has write to this, then it will successfully go through, okay? So the question, how does it, so this is all hardware level. So this is actually within the ISA, okay? So it's actually, think about this as a flag that there is this particular instruction that's kind of, that's going to be equal to 1. Yeah. Yeah, you just replace 1 with 1. So what will happen is, the question is like, if the lock is already acquired, it means that it's already 1. So you're reading 1 and writing 1, nothing bad happens. But what will happen is that you're not getting the 1 value. You get you get the 1 value and you're going to return 1, and 1 means that, oh, I don't have it. Mm-hmm. So this one is more of a bit, so this one and this one is not exactly the same thing. This one is kind of like busy looping all the way, okay? Or instead of like doing the busy loop, you can just, instead of going back to the load, here you can just return 1 or 0. So you return 0 only if this is success. You return 1 if it's not a success, okay? So it's kind of like the same thing here, yeah? So this implementation is more of a busy looping, but you can get rid of this, and then just return the value 1 as a not successful and 0 as a successful. All right, so this is kind of like just describing what I said. On load link, processor remembers the address, then checks that if there is any write by other process. If the other writes are detected, it's going to fail the store conditional. And actually, the nice thing about this is actually can be implemented using coherency protocols. If we have an exclusive state, moving from E to S or M is an indication that somebody else is writing, okay? So a store conditional, all it needs to do is really checking the state of your cache coherency protocol. If it's E and stays in E, it means that you're the only one who has this, so you can just continue doing it. If it moves to S, then that's the indication that somebody else is writing and we have a problem, okay? Okay, let me just quickly finish this because that's the end of what is going to be included in your quiz. So we talked about locks, and this usually we use locks with release consistency. So instead of having a sequential consistency, we can have mutual exclusiveness with release consistency. There's a whole bunch of optimization. So instead of test and set, we can have test and set. There's a whole bunch of things, including fairness between locks, avoiding deadlocks, and so on and so forth. We're not going to talk about these things, so we don't have time for it. But just keep in mind that just general idea of synchronization and mutual exclusiveness is a vast area. Lots of research is doing there. So again, if you're interested, go and check them out. Bottom line is that the range of possibilities, there are exclusiveness, barriers, fences, memory models. Just don't be confused between them. you need all of them in order to make sure that your program works, okay? So you have to have a good understanding of all these possibilities. At the end of the day, it's the developer that needs to understand this and needs to apply this, okay? That's it. Thank you, guys. See you.